If I told you that energy, the most fundamental concept in all of physics, might not actually be conserved? That the universe could be creating energy out of nothing right now, in violation of everything you learned in school? Stephen Hawking didn't just bend the rules of physics. He shattered them in ways that make most scientists deeply uncomfortable, revealing that energy itself behaves in impossible ways that rewrite the very foundations of reality. Before we dive into this revelation that challenges the most sacred law in all of science, hit that subscribe button immediately, because what you're about to learn will completely overturn your understanding of how the universe works. And trust me, once you see what Hawking discovered about energy, you'll never look at existence the same way again. This isn't just physics. This is heresy that happens to be true. Let me start with something you probably think you understand. Energy cannot be created or destroyed, only transformed. The law of conservation of energy. It's taught in every physics class. It's one of the bedrock principles of science, and it seems to be confirmed by every experiment we've ever done. Burn wood, and the chemical energy becomes heat and light. Drop a ball, and potential energy becomes kinetic energy. Build a battery, use a battery, and energy just moves around, never appearing or disappearing. This law is so fundamental that violating it would seem to break reality itself. Stephen Hawking proved it's violated, constantly, everywhere. And the implications are so staggering that physics is still struggling to fully accept them decades later. Here's what makes this so revolutionary. Hawking didn't just find some obscure edge case or theoretical loophole. He showed that in our actual universe, with its expansion and its quantum nature, and energy conservation as we understand it simply doesn't hold. The universe is creating energy out of nothing. Black holes are destroying energy into nothing. And the mathematics that describe this are ironclad, derived from our best theories of gravity and quantum mechanics. This isn't speculation. This is what the equations demand. Before we go deeper into this rabbit hole, I'm curious. Where are you watching this from right now? Drop your location in the comments. I want to know where in the world people are having their fundamental assumptions about physics challenged. Are you in Berlin, Bangkok, Buenos Aires? Let me know, because what we're about to explore affects every particle in the universe, including the ones making up your body right now. Let's start with the discovery that made Hawking famous. Black holes emit radiation. Before 1974, physicists thought black holes were perfect one-way streets. Matter and energy fall in, nothing comes out. The black hole just grows, accumulating more and more mass and energy forever. Then Hawking did a calculation combining quantum mechanics and general relativity, and he discovered something impossible. Black holes glow. They emit radiation, now called Hawking radiation, and as they emit this radiation, they lose mass. They evaporate. Here's the problem that nobody talks about enough. Where does the energy for Hawking radiation come from? The naive answer is that it comes from the black hole's mass, since the black hole shrinks as it radiates. But look closer at the mechanism. Hawking radiation is created by quantum fluctuations near the event horizon. The vacuum of space isn't truly empty. It's seething with virtual particle pairs that pop into existence and immediately annihilate. Near a black hole's event horizon, sometimes one particle falls in while the other escapes. the escaping particle becomes real Hawking radiation. Now here's the kicker. The particle that falls into the black hole has negative energy from the black hole's perspective. It's not bringing energy into the black hole, it's taking energy away. So the black hole loses mass, not because energy is leaving, but because negative energy is entering. This is already weird, but it gets weirder. The particle that escapes the Hawking radiation we observe, where did its energy come from? It was created from the vacuum. Energy literally appeared out of nothing, compensated by negative energy entering the black hole. This violates energy conservation, not in some technical sense that can be explained away. Genuinely violates it. Energy is being created. The total energy of the universe is changing. And Hawking proved this mathematically, rigorously, using the best physics we have. Most physicists, when confronted with this, try to save energy conservation by arguing that if you account for the gravitational field properly, everything balances out. The energy of the radiation is offset by changes in the gravitational field, so total energy is conserved. Hawking himself went back and forth on this, but here's what he eventually realized, and what makes his position so radical. Asking whether energy is really conserved depends on how you define energy in a curved, dynamic spacetime. And there's no unique way to define it. In flat, unchanging spacetime, energy conservation is clear and unambiguous. But in the universe we actually inhabit, spacetime is curved by mass and energy, and it's expanding. In such a universe, there's no single, agreed-upon definition of total energy. Different definitions give different answers about whether energy is conserved. This isn't a failure of our mathematics. It's a fundamental feature of general relativity. Energy conservation, the most sacred law in physics, is only approximately true, and only in special circumstances. Let me give you an even more dramatic example. The expansion of the universe itself. As the universe expands, it's creating space. More volume is appearing between galaxies. Now that space isn't empty. It contains quantum fields, including the electromagnetic field, the Higgs field, and others. These fields have energy, what's called vacuum energy, or zero-point energy. As space expands and creates more volume, it's creating more vacuum energy. Energy is literally being created out of nothing as the universe expands. Wait, it gets even better. Dark energy, the mysterious force accelerating the universe's expansion, has a fixed energy density. That means as the universe expands and creates more volume, the total amount of dark energy increases. The universe is not only expanding, it's filling that new space with energy that didn't exist before. Energy is being created continuously, everywhere, at every moment. The universe is violating its own most fundamental conservation law on the largest scales imaginable. Hawking understood this deeply and grappled with its implications throughout his career. He realized that energy conservation is not a fundamental law. It's an approximate rule that emerges in certain situations: flat spacetime, small regions of curved spacetime, short time intervals. But when you look at the universe as a whole, evolving over billions of years with spacetime dynamically curving and expanding, energy conservation breaks down. It's not fundamental, it's emergent and approximate. This is profoundly unsettling for physics. Energy conservation is tied to time symmetry through Noether's theorem. If the laws of physics don't change over time, then energy is conserved. But in an expanding universe, the geometry of space-time is changing over time. There is no time symmetry. Therefore, by Noether's theorem, there's no reason to expect energy conservation. And indeed, we don't have it. I want to pause here and ask, how does this make you feel? Does knowing that the universe is creating energy out of nothing, violating what seemed like an inviolable law, does that excite you or unsettle you? Drop a comment right now, because we're about to go even deeper into how Hawking's insights about energy remake our entire understanding of physics. Let's talk about another way Hawking showed energy behaving impossibly: the temperature of black holes. When Hawking calculated that black holes emit radiation, he found they have a temperature inversely proportional to their mass. Smaller black holes are hotter. As they evaporate and get smaller, they get hotter and radiate faster, creating a runaway process. Eventually, a black hole radiates away all its mass in a final burst of energy. Now think about what this means. A black hole is a region of space-time so curved that nothing can escape from inside the event horizon. All the mass and energy inside is trapped forever, or so we thought. But Hawking radiation means that black holes aren't eternal. They evaporate. The energy that fell in comes back out, but in a different form, completely scrambled and thermalized. Here's the energy problem. Suppose you drop an encyclopedia into a black hole, or better yet, a hard drive containing terabytes of information. That information represents a very specific, low-entropy configuration of matter and energy. The black hole absorbs it, and eventually the black hole evaporates, emitting Hawking radiation. That radiation is thermal, random, maximum entropy. The information seems to have been destroyed, but quantum mechanics says information cannot be destroyed. This is the black hole information paradox, and Hawking spent decades wrestling with it. His final answer, which he only reluctantly accepted, is that the information is preserved, but in a way that seems impossible, by classical physics. It's encoded in correlations between the Hawking radiation particles in a way that's so scrambled, it's practically impossible to decode. What does this have to do with energy? Everything. Because preserving information while radiating thermally requires physics beyond what our current theories allow. It requires the inside and outside of the black hole to be entangled in ways that violate locality. The principle that distant regions of space can't instantly affect each other. The energy of the Hawking radiation has to be correlated with the energy of stuff inside the black hole, even though they're separated by an event horizon that nothing can cross. Hawking eventually concluded that black hole evaporation requires quantum gravity, a theory we don't yet have. The energy accounting only makes sense in a framework that unifies quantum mechanics and general relativity. In our current theories, taken separately, the energy behavior of black holes is simply impossible. They do things energy isn't allowed to do. Let me share another example that Hawking explored extensively: vacuum energy and the cosmological constant. Einstein introduced the cosmological constant as a fudge factor to make the universe static, then called it his biggest blunder when the universe turned out to be expanding. But modern cosmology brought it back as dark energy. And here's where things get really strange. The cosmological constant represents the energy density of empty space itself. Quantum field theory predicts this should be enormous, something like 10 to the 120th power larger than what we observe. This is the worst prediction in the history of physics. The observed dark energy is tiny compared to what theory says it should be. Why? Hawking worked on this problem and proposed that maybe we're asking the wrong question. Maybe vacuum energy doesn't follow the same rules as other forms of energy. Maybe it's not conserved, not quantized, not even positive definite. Maybe the vacuum is doing things with energy that violate all our assumptions. We don't know. We can't calculate it from first principles. The energy of empty space is behaving in ways our theories don't predict and can't explain. What's fascinating is that Hawking didn't see these violations of energy conservation as problems to be solved by patching our theories. He saw them as clues that our understanding of energy itself is incomplete. Energy, he argued, is not a fundamental substance. It's a bookkeeping device, a way of tracking how systems evolve. And in extreme situations, curved space-time, quantum gravity, cosmological scales, our bookkeeping breaks down because the assumptions underlying it no longer hold. This is a radical reframing. Most physicists treat energy as a real physical thing that exists in the universe and follows conservation laws. Hawking increasingly saw it as a mathematical construct that's useful in many situations, but doesn't have the fundamental status we ascribe to it. It's closer to a model or a description than to an intrinsic property of reality. Think about what this means. If energy isn't fundamental, what is? Hawking's answer draws on information theory. Maybe information is more fundamental than energy. Maybe the universe is fundamentally about the processing and transformation of information. And energy is just one way that information manifests in physical systems. This connects to his late career focus on the holographic principle and the idea that the information content of a region of space is proportional to its surface area, not its volume. Where are you watching from, by the way? I asked earlier, but I want to check in again. Drop your location in the comments. This conversation about the fundamental nature of energy is happening globally, and I'm curious how people from different scientific and cultural backgrounds are processing these ideas. Now let me take you to one of the most mind-bending implications of Hawking's work on energy: the possibility of creating universes in the laboratory. This sounds like science fiction, but Hawking took it seriously based on his understanding of how energy works in quantum gravity. In standard physics, creating a universe would require infinite energy, because you'd need to create all the matter, all the space, everything from nothing. But Hawking realized that in general relativity, gravitational energy is negative. The negative gravitational energy can exactly cancel the positive matter energy. The total energy of a closed universe could be exactly zero. If the total energy is zero, then creating a universe doesn't violate energy conservation, even in its conventional form. You're creating positive energy in the form of matter and negative energy in the form of gravitational attraction, and they sum to zero. A universe is the ultimate free lunch, as physicists sometimes say. And if creating a universe requires zero energy, then maybe it could happen spontaneously through quantum fluctuations, or maybe advanced civilizations could do it deliberately. Hawking explored these ideas in his work on quantum cosmology and the no-boundary proposal. He suggested that the universe could have spontaneously appeared from nothing, without violating any conservation laws, because its total energy is zero. The Big Bang wasn't the injection of energy into the universe. It was the separation of energy into positive and negative components that exactly balance. This is mind-blowing on multiple levels. First, it suggests the universe literally came from nothing, not as a miracle, but as a quantum event allowed by the laws of physics. Second, it implies that energy, even in its conserved form, isn't really conserved in the deepest sense, because you can create positive and negative energy together out of nothing. Third, it raises the possibility that our universe might not be unique, that other universes could be created the same way, either naturally or artificially. Let me share my personal take on this, and I really want to hear what you think. I believe Hawking's insights about energy are liberating rather than disturbing. We've been treating energy conservation as a sacred, inviolable law, but Hawking showed it's more like a useful approximation that works in everyday situations but breaks down at the extremes. This doesn't make physics arbitrary or unreliable. It makes physics more subtle and interesting. The universe is not constrained by the simplistic rules we teach in introductory classes. It's far stranger and more creative. What do you think? Does learning that energy conservation is violated in fundamental ways make the universe feel more chaotic? Or does it reveal a deeper order beneath our simplified models? Comment below, because I think this is one of those questions where thoughtful people can disagree, and the discussion itself reveals different ways of thinking about physics and reality. Let me continue by exploring one of Hawking's most controversial proposals: negative energy. In quantum field theory, energy can be temporarily negative due to quantum fluctuations. These violations are tiny and fleeting, constrained by the uncertainty principle. But Hawking suggested that in certain circumstances, stable configurations of negative energy might be possible. Why would you want negative energy? Because it could allow things that seem impossible. Wormholes, shortcuts through space-time, require negative energy to hold them open. Warp drives faster than light travel without actually exceeding the speed of light require negative energy. Time machines require negative energy. All the exotic technologies that science fiction dreams about require violating the assumption that energy must be positive. Hawking initially proved that closed time-like curves, paths through space-time that loop back on themselves allowing time travel, are impossible if you assume various energy conditions that forbid negative energy. But then he started questioning those energy conditions. Quantum mechanics allows temporary negative energy. What if you could stabilize it? What if advanced technology could manipulate quantum fields to create regions of negative energy? He never found a definitive answer, but he opened the door to thinking about energy in ways that classical physics forbids. And some physicists have since found theoretical configurations, like the Casimir effect between conducting plates, where negative energy density appears to be real and measurable, not just a quantum fluctuation. This is classic Hawking, taking seriously the implications of our theories even when they lead to uncomfortable or seemingly impossible conclusions. If the math allows negative energy, even in principle, then we should explore what that means rather than dismissing it out of hand. Another area where Hawking pushed beyond conventional energy physics is entanglement and non-locality. Quantum entanglement links particles across arbitrary distances, such that measuring one instantly affects the other. Einstein hated this, calling it spooky action at a distance. But experiments have confirmed it's real. Now here's the energy puzzle. When you measure an entangled particle, You can't use entanglement to send information faster than light, which would violate relativity. But something is happening faster than light. The particles are coordinating their behavior across space instantaneously. How is this possible without violating causality and energy conservation? Hawking worked on reconciling quantum mechanics with general relativity, and entanglement was a key puzzle. His insight was that entanglement doesn't transfer energy or information in the usual sense. It's a correlation, not a causal connection. The particles aren't sending signals to each other. They're both connected to a shared quantum state that transcends space. But this raises profound questions about what energy even means in a quantum context. If entangled particles can affect each other without it exchanging energy, then energy transfer isn't the whole story of physical causation. There are other channels of influence that our energy-based accounting doesn't capture. This suggests again that energy is not as fundamental as we thought. Let me give you another example from Hawking's work: virtual particles and the quantum vacuum. In quantum field theory, the vacuum isn't empty. It's filled with virtual particles constantly popping in and out of existence. These particles exist for such short times that they don't violate energy conservation in any measurable way. But they're real enough to have observable effects like the Casimir effect and the Lamb shift. Hawking took these virtual particles seriously as physical entities, not just mathematical conveniences. And this led him to radical conclusions. If virtual particles are real, and they're constantly being created and destroyed, then the vacuum is seething with energy. How much energy? Naively, infinite. But clearly, the vacuum doesn't have infinite energy, or the universe would be very different. This is another place where our understanding of energy breaks down. The energy of the quantum vacuum should be infinite by our calculations, but it's observably finite and small. We don't know why. We can't calculate it. The energy of empty space is doing something our theories don't predict. And Hawking saw this as a deep clue that we're missing something fundamental about how energy works. Hawking also explored the energy implications of the multiverse. If there are multiple universes, each with different physical laws and different amounts of energy, then energy isn't conserved across the multiverse, only within each individual universe. And if universes can branch off from each other or interact, as some quantum interpretations suggest, then energy could flow between universes in ways we can't detect or measure. This sounds speculative, and it is, but it's grounded in serious physics. The many worlds interpretation of quantum mechanics, which Hawking found appealing, suggests that every quantum measurement causes the universe to branch into multiple versions, each experiencing a different outcome. Where does the energy come from to create these new universe branches? The answer, if you take many worlds seriously, is that energy is conserved within the wave function of the entire multiverse, but not within any individual branch. From our perspective, stuck in one branch, energy appears to violate conservation at every quantum measurement because we're only seeing part of the total system. The energy we lose goes into other branches. The energy we gain comes from other branches. This is profoundly strange, but it's what the mathematics of quantum mechanics suggests if you take it literally without imposing wave function collapse. Hawking was willing to follow the math, even to conclusions this bizarre. Let me ask you something. Where are you watching from right now? drop your location one more time in the comments if you haven't already. I want to build a global conversation about these ideas, and I'm curious how people from different educational and cultural backgrounds are responding to Hawking's radical reimagining of energy. Now, here's where Hawking really went beyond what science conventionally allows. He suggested that consciousness might play a role in energy dynamics. This is incredibly controversial because it sounds like mysticism, and Hawking was a strict materialist who had no patience for supernatural explanations. But he took the measurement problem in quantum mechanics seriously. In quantum mechanics, systems exist in superposition until measured. The act of measurement collapses the superposition into a definite state. But what counts as a measurement? Does it require a conscious observer? Many physicists say no, any physical interaction counts as a measurement. But some interpretations, including ones Hawking explored, suggest consciousness plays a special role. If consciousness does play a role in collapsing quantum states, and collapsing quantum states involves selecting one energy eigenvalue from many possibilities, then consciousness is involved in determining the energy content of the universe. Not creating energy out of nothing in a mystical sense, but participating in the physical process by which potential energies become actual. Hawking never fully committed to this interpretation, but he didn't rule it out either. He recognized that the relationship between quantum mechanics, consciousness, and energy is one of the deep unsolved problems in physics. Our theories work brilliantly for calculating energy in physical systems. But when you probe the foundations deeply enough, consciousness keeps appearing in ways that are hard to dismiss. Another frontier where Hawking pushed energy physics beyond conventional limits is in his work on thermodynamics and information. The second law of thermodynamics says entropy always increases. But entropy is related to information, and information is related to energy through Einstein's E=mc2. If you can manipulate information, you can manipulate energy in ways that seem to violate thermodynamics. Hawking showed that black holes have entropy proportional to their surface area. This black hole thermodynamics connects gravity, quantum mechanics, information, and energy in a deep way we still don't fully understand. It suggests that, at the most fundamental level, the universe is not about particles and fields and energies. It's about information being processed. And energy is just one manifestation of information dynamics. This information theoretic view of energy has profound implications. It suggests that energy conservation might not be a fundamental law, but an emergent property of information conservation. If information cannot be destroyed, and energy is a form of information, then energy conservation follows. But in situations where information can be created, transformed, or lost in ways we don't fully understand, like in black hole evaporation or cosmic expansion, energy conservation breaks down. Let me bring this back to something more concrete and personal. Every thought you have, every action you take, involves energy transformations in your brain and body. The food you eat is converted to ATP, which powers neurons, which generate thoughts and movements. This is standard biochemistry. But Hawking's insights suggest that even these everyday energy processes might be more mysterious than we think. Your brain is a quantum system. It operates at temperatures and scales where quantum effects could be relevant. If consciousness involves quantum processes, and if quantum processes allow energy violations through uncertainty and entanglement and measurement, then your thoughts might involve subtle energy dynamics that violate conservation in ways too small to measure, but perhaps significant for understanding consciousness itself. This is speculative, and Hawking would be the first to admit it, but it shows how his willingness to question energy conservation at fundamental levels opens up new ways of thinking about everything, including life and mind. Throughout his career, Hawking returned again and again to the question, what is energy really? Is it a substance, a property, a mathematical construct, a form of information? His answer evolved over time, becoming progressively more abstract and less tied to our intuitive notions of energy as something that flows and transforms, but always remains constant in total. By the end of his career, Hawking seemed to view energy as an effective description that works in certain regimes, but breaks down when you probe deeply enough. It's like how solid matter seems continuous at everyday scales, but is actually made of discrete atoms. Energy seems conserved at everyday scales, but might be emergent from deeper, more fundamental principles that don't respect conservation. What are those deeper principles? Hawking had ideas involving quantum information, holography, and the fundamental nature of spacetime, but he never had a complete answer. This is the frontier of physics, where energy meets quantum gravity, and we're still groping for understanding. One of the most beautiful aspects of Hawking's approach is his willingness to say, "I don't know." When confronted with energy violations that our theories can't explain, he didn't paper over the cracks. He highlighted them, explored them, and used them as guideposts toward deeper understanding. The places where energy conservation breaks down are precisely the places where new physics awaits discovery. Let me share a final thought on why Hawking's insights about energy matter beyond pure physics. If energy is not absolutely conserved, if the universe can create it out of nothing, if it behaves in impossible ways at extremes, then the universe is more creative, more generative, more fundamentally productive than we imagined. We're not living in a closed system with a fixed energy budget slowly running down to heat death. We're living in an open, dynamic, creative universe that's constantly doing things our simplified models say it can't do. This has philosophical and even spiritual implications, though Hawking himself was an atheist. The universe doesn't just shuffle around pre-existing energy. It creates novelty. It generates new possibilities. It's not a mechanism grinding toward equilibrium, but a creative process unfolding in ways we're only beginning to understand. Before we close, make sure you're getting everything from this content. If this video changed how you think about energy, physics, or the nature of reality, hit that like button. If you want more content exploring the cutting edge, where science meets philosophy, subscribe and turn on notifications. Share this video with someone who's ready to have their assumptions about the universe challenged. Because these ideas are too revolutionary to keep to yourself. Stephen Hawking gave us a new way of understanding energy. One that's more subtle, more interesting, and more true to what the mathematics of our best theories actually say. Energy is not the rigid, conserved substance we teach in textbooks. It's something stranger, a useful approximation that breaks down at extremes, revealing deeper principles we're still discovering. You've just witnessed physics at its most radical and most honest. Hawking didn't shy away from the implications of his equations, even when they violated sacred principles. He followed the math wherever it led, and it led to a universe where energy behaves in impossible ways. where black holes create and destroy it, where cosmic expansion generates it from nothing, where quantum mechanics allows violations we can't measure but can't deny. This is the real universe, not the simplified version we learn in school. It's weirder, more creative, more fundamentally mysterious than we ever imagined. And energy, that most basic concept we thought we understood, turns out to be one of the deepest puzzles in all of physics. Thank you for joining me on this journey beyond what science conventionally allows. Drop your thoughts in the comments. Subscribe for more content that pushes beyond the boundaries of mainstream physics. And remember, the universe is not constrained by our assumptions about what's possible. It's doing impossible things right now, every moment, creating energy where there should be none, violating laws we thought were absolute, and inviting us to develop deeper understanding that can finally explain what's really going on. Stephen Hawking showed us that energy is not what we thought it was. Now the question is, what else have we gotten wrong? What other fundamental assumptions will future discoveries overturn? The only way to find out is to keep questioning, keep calculating, keep following the math even when it leads to impossible conclusions. Because sometimes the impossible turns out to be true. And that's when science gets really interesting.